and welcome to differential equations. So, introduction to differential equations. We are going to first define differential equation, and then do classification, and then do some modeling. So that's all in the first lecture. So, differential equation is the equation which contains an independent variable, function, and its derivatives. Generally, I would say f of t, f of t, f prime of t, f double prime of t, dot dot dot, equal to 0. You are, if you took calculus 3, you are familiar with the multivariable explicit form to write a mathematical equation. Some examples for differential equation might be as simple as y prime equals to 1. This is a differential equation because you have unknown function y. You all know what that function is just by looking at it, right? But you have the unknown function y, the derivative of unknown function y. So this is an equation, and it's probably the simplest equation that you can see. But then other examples might include 2y prime minus sine t equals to 9. That is also a differential equation. You see that it contains some kind of a function, f of t, and then there is also the y prime. Again, for each one of these differential equations, function y is the unknown. We can also have 3, this would be the constant coefficient, second order constant coefficient equation. So let's say minus 4y prime plus 9y equals to 0. That is also a differential equation. All of these equations that you see as examples here are linear equations because I have done nothing to y and y primes. But I could have y prime squared minus 3y equals to sine t. Now this one would be nonlinear differential equation because we have derivatives squared. I can get more nonlinear equations by simply writing sine of y or sine of y prime. And these equations can get really crazy really fast. What we are going to cover in this course is 10% of 1% of differential equations that are out there. Whatever you see in this course is considered stuff that it's easy to compute by hand. Vast majority of differential equations are computed numerically today for applications in engineering and so on. So you can, this is a technically introductory course to differential equations. There are easily another 5 or 6 courses following this course, all on differential equations for different areas. For engineering, for mathematics, for finance and economics, right, and so on.
What does come after for like finance? If you had to leave this and go to the next one, what is it?
Well, there are stochastics methods, there are dynamical systems, there are partial differential equations. There are a lot of different applications. We can talk, if you guys have questions that pertain to your particular major and interest, like please talk to me. because I will tell you exactly what I never took any of the stochastics, for instance, because I am not too much into finance and so on. But if you are in that world, right, for analysis and the actuarial work and so on, like I know, Ryan, you are, those would be that would be one of the routes. And then you have also Fourier stuff and so on. It's electrical engineering, or so there are a lot of you have the mechanical engineering with your thermodynamics. You are talking about partial differential equations, so good luck to all of you. And a lot of good stuff coming up as you go through this.
Are you saying partial derivative? Use harder?
Partial differential equations are about 170% power series, and then negative 10% everything else. So, so that's it's a really awesome course. Yeah, where the easiest problem is like 17 pages. So, yeah. You want a cheap course, dynamical systems, then you move into biology. Yes. All right. Talking about differential equations, very important part here is to understand, and you all took Calc 2, so you know that the answer for differential equation, the unknown thing that you are looking in differential equations, is a function. That's what you're looking for. So for all of these guys here, what it boils down to is, what is y equal to? What is that f of x, right, that you are looking? You are used to basic equations. So far, when you see 2x plus 3 equals to 17, right, you subtract 3 on both sides, 2x equals 14, and then x is eventually 7. Now, think about this: exponential equations, logarithmic equations, trigonometric equations, any kind of polynomial. Any equation you solved so far, the answer was one number or two numbers or infinitely many numbers in terms of trig. All of the answers were numbers. We are going now a whole dimension higher. Your answers are going to be functions. And those functions are going to actually be mathematical models which paint the world around us. So we are going to talk about population models, economic models, engineering models, and so on. Those models will necessarily explain concept. 100% of physics is developed from differential equations. And you have seen that in your calculus course, which I will clearly redo today. So for differential equation, maybe I can just solve the basic one over there before we go into crazy things. I will write this one as dy over dx equals to 1. I will separate variables and then undo the calculation. So remember what we did here. You see me subtracting 3 on both sides because that is opposite to adding 3, which was in equation. What you have there is you have derivatives, which you create into differentials, and you undo those by integrating both sides. So you get y equals x plus c. This over here is your general solution to, we usually say ODE, ordinary differential equation, because we have differential equations like dynamical systems and so on. Ordinary, simple, right? By the way, this course is still considered as the elementary mathematics course because of its, I want to say low-level use, but we technically, as I say, we learn 10% of 1% of differential equations in the entire course. So it's still an elementary course. So this is your old equations versus differential equations. So your old answers were numbers, the new answers are functions. Now these functions will eventually generate numbers. If you are looking to put all of the mathematics into a single kind of shell, it boils to a location in space on the graph. And that's what it is. Yes?
What's the ODE mean?
Ordinary differential equation. So we have classification of linear and nonlinear ODEs. Linear would be, as I mentioned earlier, so the y prime equals 1, maybe 3y double prime minus 4y plus, sorry, y prime plus y equals to 0. Those are all linear. The nonlinear equations would look like y prime everything squared equals to cosine, let's say x is the independent variable. You would have maybe y times y prime minus x equals to 3. So nonlinear equations have these nonlinearity attached to either y or y prime. You can have x to the 100th power. If that is independent variable, it's not going to affect the differential equation. So as you can see over here, this is the second derivative, it's the first derivative, it's the original function. It's important that those are not embedded into ln's or sine and cosine. It's important that those are not squared or cubed, because that creates nonlinear elements. And here are the nonlinear elements. So this is nonlinear because of the square. This is nonlinear because these guys are multiplied. I make this one linear as soon as I put plus or minus in between them. It becomes linear immediately. So as long as each of the individual terms of differential equation has just y prime, just y double prime, just y, not embedded in any of the transcendental functions or so on, the equation is linear. We also have order of ODE, which would be first derivative, first order, so y prime, first order, y double prime, second order, ODE, and so on. So look for the highest derivative and that's equal to the order of ODE. Those of you still wondering, function is the zeroth derivative. So that's the base state. And then you have the first derivative, second derivative, third derivative, and so on. Those of you who want to learn more of interesting mathematics, you will clearly research in between derivatives. What does it mean to take a half a derivative of something or 5/2 derivative? That actually exists. So look it up. I know, it's fun. So you can look up that stuff online.
You said the function is what's the function? The zero derivative?
Yes, function is the zeroth derivative, and then you have the first and the second and the third and so on. The highest order of the derivative you have is going to be the order of the differential equation. Therefore, the order of this differential equation is the second order linear. This one will be the first order linear. This is the first order nonlinear differential equation. And this one is, well, first order because of the y prime. But then it's trickier when you start getting the y prime times y double prime and so on. Then it gets much crazier. But we don't deal with that in this class. One technique, you learned probably two techniques so far. How to solve differential equation, a graphic method, which was slope fields, and you learned separation of variables. So we will start with separation of variables, and we're also going to work on modeling at the same time. 100% of your physics is derived through differential equations. Once you are very fluent with differential equations and are able to transform text into differential equation, you don't have to remember stuff in physics anymore, because you will be able to recreate every equation there is. In differential equation, stuff starts by you realizing that there is the model to be written as a differential equations model. So we start by, let's do the most basic stuff from bio, where I'm going to say that change of population in time is proportional to population. I'm writing that sentence down. So change of population in time is proportional to population. I am struggling to keep this in one line because I need to write underneath and translate this English sentence into mathematical sentence, known as the differential equation in this case. A change of population in time. What does that sound like? Very good. It's the change of population in time. It is the derivative. The word is equal sign, constant on proportionality, usually k, and then you have times p. This is how you transform English sentence into mathematical sentence. Now you are going to hear these sentences at the meeting, and when you hear the sentence at the meeting, you're writing equation down. And then you feed that into Wolfram and you create stuff. So the most important skill that you can develop for your engineering career is to be able to translate the concept that you observe in nature into mathematical equation. Because once you have a model, you are able to quickly build things. Observe how, I will put quotes, advanced we are in terms of technology. We are able to create computers, and we are able to cell phones and cars and all of these kind of things, satellites, right? And then observe, I mean, it's nothing special, but still, all right? And then observe how pathetic we are in terms of any kind of medical stuff. You still have operations and recovery time and everything else, right? And half of the diseases we don't even know how to tackle. What is the difference between the two worlds? The world of electronics and the world of technology is 100% mathematically mapped, 100% mapped with physics, and all of that stuff, right, is working perfectly. We are creating more complex machines as we go along, but everything is 100% understood and 100% mathematically mapped. Go to the medical field. What do we have? It's technically a guesswork. We are trying to guess the cure for cancer. We are trying to guess the cure for AIDS. We are trying to guess the cure for all of these things. And then we get lucky and we discover the cure for certain things because you run these experiments on tens of thousands of trials and so on, right? But then some complicated problems we cannot figure out by guessing, and most likely we will not figure out by guessing until we have humans mathematically mapped. So when you are observing a concept of some, right, like this one, right, if it's easy to write mathematical model, you should write mathematical model because you get to understand that concept 100%. So now that I have my differential equation, I want to solve it. And we all know that we are going to use the method of separation of variables because we see that we have population showing up twice and the independent variable t showing up once. It's easy to separate variables, all p's on one side or t's on the other. And this k is the constant of proportionality. That one can go on either side, so I'm not going to touch it. So here I have dp over p equals to k dt. And now we hit this with the integral sign. Observe that k is the constant. You know that you can escape the integral sign. So I can put the integral sign before or after k. It really doesn't matter. What is the integral on the left? Very good, absolute value. So it is ln absolute p equals
Plus c.
Plus,
yes,
I was about to say that. Took it.
exactly, plus c. Now,
How do we decide which side to put the C on?
on the right. Yeah, it doesn't matter, but it doesn't matter where you put plus c. We generally put it on the right side. If you put c1 on one side and c2 on the other side, then the c is c2 minus c1, right?
Right.
So we only need one side to have plus c. If you forget plus c in differential equations class, it's not, points are off. You're technically dead because this constant has a lot of weight in this class. And you will see the difference between particular solution and the general solution is exactly the value of c. General solution, you don't know what c is. Particular solution, you know exactly what c is. Now that gives us the difference between initial value problem and the general problem. So this plus c is extremely, insanely important. Never forget plus c when you're doing these things now. That's it. Yes.
I have just a quick question on the ln. Is it because when you do absolute value, I forgot, so that's why I'm just asking.
What do you mean?
ln, it's always ln for absolute values when you do the integral.
The integral of dx over x is ln absolute x plus c. And the reason is on this side you have 1 over x, on this side you have ln. If you just have ln x without absolute values, you're running into issue with the domain. If you look at the input domain is, as you can see, positive and negative. And if you look at the output without absolute values, you would have just this, which means that you are able to plug in -7 on the left-hand side, but if you don't put absolute values, you're not allowed to plug in -7 on the right-hand side. So the absolute values are there to fix the issue of the domain so that after integration, we have the same domain on both sides. So that's the reason why we have the absolute value for this particular calculation. All right, so now we're going to e both sides. Now, when I e both sides, I don't need absolute values anymore because the ln is gone. So it's just p now. I don't have to put absolute values anymore. On the other side, I have e to the kt plus c, and this might be now the next issue. We want to simplify this as much as possible. I'm going to start writing p of t because it's a function, right, of t. You see the variable t on the other side. We know from algebra that x to the m plus n is x to the m times x to the n. So I'm going to break this part here at the plus, getting e to the kt times e to the c. And I'm going to define this e to the c as p0. We call that initial population, p naught, p0, whatever you want to call it. So our model becomes p of t equals to p0 e to the kt. Now this over here is the general solution to the differential equation. And this is where you start understanding the process from going from the model through solution through getting the answer, and now what does that answer mean? I mentioned that you should be taking limits and understanding. I'm going to actually take the limit as time goes to infinity and just see that the whole model is garbage on infinite scale, because we know that this planet cannot have infinite population of whether it's people or bacteria or rabbits. Infinity doesn't fit on the surface of the planet, that it's finite. So if I just quickly take the limit as time goes to infinity of p0 e to the kt, I see that the answer is positive infinity. We also know that exponential growth graphs this way. So we see that this model is garbage for the big picture. But this model actually works locally, right? If you want to take a look at population of humans, you know, from 1980 to 2017, the model is going to work, right? It's fine. But if you want to predict what's going to happen with the human population in, let's say, 700 years, this model is going to be garbage, complete garbage. You accumulate knowledge along this course to see which model actually works, which model doesn't work, right? And then you have to think about concepts. You have to ask yourself, well, is it viable at all for a model like this to be the only model for population of whatever you're thinking? So you're starting to now say, okay, why is this P0, right? This e to the c. Why is that called P0? Well, think about it. P0 is the initial value. It is the beginning of time, like the Big Bang for this particular population. So that is at time equals 0, right? There is no time -1 to go, right? There is a Big Bang and complete irrelevance before Big Bang. So anytime you're talking about initial value in differential equations, think of that initial value, the word initial, right? That is, think of it as a Big Bang for whatever your application is, and anything before that time is completely irrelevant to all of science, right? Whatever your concept is. So now, if I am thinking 500 rabbits, so here is the Big Bang, 500 rabbits are there, right? Now, at Big Bang, t is equal to 0 because that is when everything begins. I have 500 rabbits at the beginning of time. T equals 0 would make all of this 1, right? So you see that in the initial case, when time is 0, this is the entire initial population. So that's why we label it as P0. At initial time, you have initial population. Bueno? And initial time is always t equals 0. Hence the word initial, right? It starts there.
I was just wondering, we're starting at the Big Bang. We haven't had people for, what, millions of years after the Big Bang? How would that?
Well, there's evolution in between.
Metaphor,
This is the metaphor. This is the Big Bang for 500 rabbits.
Oh.
So you open the classroom door and it's 500 rabbits.
Okay.
You just created the Big Bang situation for that room, right? And now we're going to observe that population evolve in time. Right? Kevin, you're hopefully making a rabbit now. So now we are going to take a look at our model and see that if this model even remotely is getting is giving us anything, right? So
when t equals 0, though, what about k? It's not, e isn't going to go to 1. If t equals 0, k is something. It's not going to go to 1.
Well, t is 0. K can be anything other than infinity, right? K is the constant of proportionality. Okay. So that cannot be infinite. Okay. You cannot have infinite proportion. So that's going to be negative 0.3 or it's going to be positive 300. 0 is going to kill it.
Okay, right.
So you have e to the 0 is 1, so initial case is there. Now, let's take a look at all of these guys, right? So this is the population at any moment in time. Whatever you plug there, right, will compute the population, which is that t. This is going to be fixed to whatever your Big Bang population was, which is, let's say, 500 rabbits. What is this k? Constant of proportionality. This k could easily be 0. I can walk into the classroom at the Big Bang for rabbits and just find 500 female rabbits. If there is 500 female rabbits, are there ever going to be, or male rabbits, whatever, are there ever going to be new rabbits? No. You need a male and a female, right? So, if it's all the same sex, there's not going to be more. So, having the same sex rabbits for the entire initial population immediately makes k 0, because it's not going to change. You cannot change population if you have only one sex. Now, if you have whatever the proportion would be, right? I would assume you would need less male rabbits than female rabbits. Then you can actually figure out, using biology observation or whatever statistics, you can figure out what is the appropriate proportion between the male and female, which would raise this to the maximum point. That would maximize this number when it's multiplied into the, yes?
So let's say we go back to the example of the 500 male rabbits. Then can we, over time, we'll see them die off.
Well, let's say that's a 500 immortal rabbits. 500 elf rabbits, okay? They are eternal.
Okay, so they're going to stay the same.
And unless they leave, they're just going to stay there forever. Exactly. They don't even need food, and they have no natural predators because they are eternal.
Well, they are.
It's a holy. I don't know if you ever seen the right. There is a. Well, there is one in if you see in the Monty Python, right? When they use the holy hand grenade.
Yeah.
So that rabbit.
That rabbit with
yeah.
the red eyes. Yeah.
Yeah. That's
Three,
so.
not
Yeah,
five,
that's what we're
not
talking
two.
about. That's what we were talking about.
Okay, so oh god, 500. Jesus.
Yeah, I'm looking at that half of the class, was like, what the hell is the holy hand grenade? Like, okay. Yeah. Catch up with reference. What can I say? So that's it. Now you can translate this to bacteria. You can translate this to people, and so on. The most important part here for me is this limit at the bottom, because the limit shows that if you are to wait infinitely long, right, the population goes to infinity, which we know it would not happen. Now, generally, when you observe situation in nature, you don't want to write everything immediately and then try to solve this master differential equation, which generally are really, really evil. You start building equations up. You see, we start with this model up there, which says, you know what, the change in population of rabbits just depends on the ratio between male and female, right? If we have mix, and then the number of 500, right? Because if you only have 2 rabbits, one male, one female, right? I don't know how many baby rabbits are there, but it's going to be much less than if you have 250 male rabbits and 250 female rabbits, right? The population will be changing faster, right? So when you look at that, this is how you start. And then you start adding different parameters to it. Maybe I want to say plus, and then I say plenty of food plus something. And then I decide to move them into an environment, right? I solve that first. And then I say, okay, so now I know how to do that. Let me move them into an environment where I have the fox and I have the hawk and I have, right, snake, right? So now the rabbits start dying as well. So we introduce the factors, and we call those predator-prey models, and you know, you can develop more robust models from there, which are much harder to solve than this initial case that you deal with separation of variables. So the same thing in engineering. In engineering, you might need a system that will have, I don't know, 3 pulleys and 5 springs for some mechanical device. You solve one pulley system, you solve a spring and a pulley, you solve 2 springs and a pulley, 2 springs and 2 pulleys, and so on. You keep building up, rather than writing one overall equation and then trying to, you know, figure out how to do that. The most important skill, I hope someone teaches you this in your engineering courses, is to never work on the entire problem. Start small, start simplify, and keep building it up. That's how you deal with any type of a problem. Also, studying this course is going to be the same thing. If you have issue with anything on that board, differential equation is going to be secondary because you can't solve any of the problems. This is what 1 plus 1 for algebra is. Right? So we start building it up and we go from there. Now, I said before something about physics. Knowing differential equations allows you to be much lazier in those courses because you understand the world much better. Say that you understand that gravity is acceleration. So you start by claiming that acceleration is negative g, right? So you start by claiming that acceleration is negative g. Why negative? Because you have the center of mass for massive objects like this planet, which is at the center of the planet. And the gravitational pull pulls towards the center of the planet. Now, us standing at the surface of the planet, we are constantly pulled down. And that's why we stay on the surface of the planet. If the more massive object passes by Earth, we would be immediately be attracted to the other more massive object. You know that tides, right, depends on the position of the moon, right? Because as the moon go over the ocean, it lifts the ocean, right? It doesn't suck it up to the moon. It lifts it 1, 2, 3 feet up, right? And we call that tide. So when you start looking at this, it's always going to be negative g because it always pulls down, because the center of the Earth is always underneath you, directly underneath you. You're always tangential and perpendicular to the tangent line of to the surface of the Earth, no matter where you are. So I'm going to write this A as change in velocity over change in time, because that's what acceleration is. You know, you have your car, you have your gas pedal, that is acceleration, accelerator. It changes your velocity. And the brake is also acceleration. We call it deceleration. So if your acceleration A is the gas pedal, then your brake is negative A. Their job is to change your velocity, change your speed, right? So what is acceleration? It's change of speed in time. There is always that lag time between you seeing a cop, right, who's measuring, and actually getting down to the speed you should be going at, right? with all the cursing in between. So that change in acceleration does not happen instantaneously. It takes time. So this is why we say change of velocity in time. And that's applying brakes. Now, you are looking at the differential equation. It's the first order. It's linear differential equation. Negative g is a constant. I could have put 6 there, right? So we are going to separate variables again. And we're going to get dv is equal to negative g dt. Boom. Right? Integral sign on both sides. And what I get is that v is equal to, on the other side, I have negative gt plus some constant c. There we go. Now, remember the beginning of time, right? When t is equal to 0, this term dies. So what is c? V. It's initial velocity. This is the type of dimensional analysis that you have. It has to be common sense to you. If t is 0, it's going to be a big bang for this. So t equals 0. That kills this term. You have a v equals c. So I'm going to call this c v0. That's just, in my view, common sense. So now what I have is the equation which says v, you can say of t, is equal to negative gt plus v0. You know this equation? Of course you know this equation. You've seen it in physics probably with v final is equal to v initial plus acceleration times time, or something along those lines, right? You recognize that equation from physics. This is how you get it.
What's the one on the right? V of that?
V final is equal to v initial. Depends on, I don't know, different books in physics will write it differently. Yeah, so this is in physics, right? We are going to use this. That's what we care about. But the physics might write something along those lines. So now you are looking at the at these equations here, and you're looking at these equations, and you start recognizing them in physics, if you took physics before. Then you look back at your original v equation, and you say, but wait, velocity is change of what in what? Change of position in time, right? Velocity is change of position in time. My position is in this classroom. And if I want to go, I mean, I don't want to, but if I want to go to the printer over there, what's my velocity right now? 0. You see that in order for me to get there, my velocity has to change. So I have to put in some acceleration. And then that velocity is going to be change in time. Also, you know velocity is miles per hour. Miles is distance, hour is time. Distance over time, it's distance. Change of distance in time. So, ds dt, I get the position, right? Position, s. Clearly, that's why the variable is s. It has s in the word position. You don't want to use p because it would be too obvious. So change of position in time is equal to negative gt plus v0. We observe variables t, that's our independent, right, the time, and then obviously position, which is our variable s. So separation of variables will give us ds is equal to, in parentheses, negative gt plus v0 dt. And then we integrate both sides again. How's the stream doing? We good? Yeah. Someone should be watching the streaming class, so to notify me if, thank you, if it dies. The integral of position is just going to be s, which is s of t, right? Position function. And then we have negative g t squared over 2 plus V0 t plus c.
Hey, that looks familiar too.
Exactly, parabolic motion, right? So now, when you look at this, you fix it a little bit. S of t is equal to negative 1/2 gt squared plus V0 t plus, at the beginning of time, when t is 0, these two terms die, and c is equal to what? S0, yes, initial position. You know this equation as well. This equation models, let's do the experiment. Everyone, look at the marker. It's going to fly. So, parabolic motion. It observed that it's negative t squared, which means on the position function, it better look like that. And we know that's exactly what we're going to get when I throw this marker, right? There's no way that I can throw this marker diagonally or anything like that, because it has to end with parabolic motion. Yeah, I can, you know, throw the marker like this and it will go the straight line right with the initial, but gravity will eventually win and it will go down. Unless, I mean, obviously I can do that, but I don't want to. Unless I throw it at 7 miles per second, then that's the escape velocity from the planet, which means it's going to hit the moon. Oh, it's less than the rocket, so nothing to worry about. If it's a 7 miles per second for the, you know, for the SpaceX rocket, I know. Can you imagine 7 miles per second? I know. And then please realize that that's pathetic.
Yeah.
Please. 7 miles per second is pathetic. This is where we are as a species right now. Make that peace. We are insignificant in every aspect of existence. All right? We think that the 60 miles per hour is a lot, and then we have a 65 mile per hour speed limit on the highway, and we call it a highway. If you are to drive 60 miles per hour in the orbit of Earth around the sun, you take the same path at 60 miles per hour, which we all go, woo, right? The planet will catch up and crush you and kill you 1,111 times, okay? That's how pathetic 60 miles per hour is, all right? In comparison to how fast the planet goes. So, yeah. Anyway. So we have these calculations. You see where physics comes from. Guys, I got all of those equations from here. We just said that acceleration is negative gravity, whatever. For different planets, for different size of the planets and stars, the gravity is going to be different. We know 9.81 on average on the surface of the planet Earth, right? And then you start like, what is it? For Mars is 6 something, 6.5, I think. So one of the issues of obviously of colonizing Mars is that whoever goes there, gets born there, the people will actually evolve to be different. Probably would be able to be taller and everything than we are. Yeah. But they would be weaker as well, yeah. So, because the gravity is different. So colonizing Mars is not just how to get there, which again, our pathetic technology at the time is a slingshot off of the moon. That's how you get to the Mars. But then, once you get there, what are you going to do with all of the, right? What are you going to do with all of the issues with, you know, gravity being worked and, you know, getting the plants to grow and so on. So, you know, the Martian thing, I mean, it's a cool movie, but when you go from Earth there and you realize that you can jump 10 feet in the air and then when you fall down, yeah, your hips are already in your neck. So good luck with all of those things. All right. Moving on. A lot of other cool applications that you can think of from Newton's law of cooling to figure out how to make a Thanksgiving turkey to, you know, technically cooling off the coffee or anything like that. There is a lot of stuff that you guys can work on in terms of these models. What I am interested in is the, let me just find, I just want to see if anything is changed. We talked about all of these things. Okay. So the next concept, and I really need you to pay attention here because this is going to be for the rest of the course, is the idea of checking your answer, because this course is a course on equations, and equations can be easily checked. So say my differential equations was dp over dt is equal to kp, and its solution was p equals p0 e to the kt. So I have the equation and I have its solution. How do I check? Well, plug in. That's how you check equations. Remember when the life was like this, x plus 3 equals to 5, and you subtract 3 on both sides, and you get x equals to 2, and then you check 2 plus 3, is that 5? 5 equals 5, right? So this was your life at my life too, at some point in time. The Big Bang of this. So that was life at some point. Now you have different variables. You have the function, which is this thing, and then you have the derivative, which is the derivative of this thing. So in order for you to check this problem, you have a little more work, but it's the still same concept. So I'm going to find the derivative, which in this case is clearly p0 k e to the kt, right? The derivative will, the chain rule just push down k. p0 is a constant which you copy. And now you have these two things to plug in. So plug both into dp over dt equals kp. So now, instead of dp dt, I have po k e kt is equal to k times, and instead of p, I have po e kt. Do we see that the sides are equal? That's it. For the second degree equation, it's going to take you a little bit more work. So say you have y double prime minus y is equal to 0. Say this is the equation. Clearly it's a second order equation. My claim is that the solution for something like this is y equals c1 e to the t plus c2 e to the negative t. I hope. Yep. So now what do? You want to check, right, if this is correct, because why trust me, right? I'm giving you the general solution, but then you don't know how to solve this yet, but you have the solution, so you can at least check. So you will find the first derivative, which is as is, except this one becomes a minus here because of the chain rule on the negative t exponent. And then you find the second derivative because the second derivative is the one you have to plug in. So c1e to the t plus c2e to the negative t. Well, it turned out that these two are the same. And now when you subtract them, you do get 0, right? So that plugs there, and you get your c1e to the t plus c2 e to the negative t minus c1 e to the t plus c2 e to the negative t equals 0. 0 equals 0. Check. Yes? P0 is a constant. We copy it. Right? Actually colors. This was replaced by this, which is here. And this was replaced by that, which is here. Bueno. So you just chase the variables, functions around, and eventually works out. Great. Any other questions, concerns? We see differential equations easy, clear. Nothing to worry about yet. What time do we end? 7:20. 7:20? Oh, then better. The next part is the talk on obtaining C, calculating C. So, as we do this, let's say I have an equation that says y prime is equal to x squared. We immediately write this as dy dx equals to x squared. Separate variables to get x squared dx. Hit both sides by the integral and obtain y is equal to, thank you, plus c. This is known as general solution. And if you are to plot this, you will have to draw infinitely many cubic functions everywhere. And the reason is that all of these functions are answers because what is the why? What is the purpose of this plus c? What does it do? The plus c, you learned this in your PreCalc 1 class. What happens when you put plus or minus constant? What happens to a function? Shifts up and down. That's all it does. So in this case, if c is 0, then you have the one that goes through 0, right? But then as soon as your c is plus 1 or minus 10 or whatever, it's going to be somewhere. The general solution will always give you infinite stack of whatever your function is. Those could be your exponential function stack, like what we had for the population thing. Or it could be the quadratic stack, right? Because guys, think about it. It matters where I throw this marker. I mean, from which height I throw this marker. That's your S0, which was your plus c. This over here is plus 7. Right? I'm 6 feet tall, plus 1 foot. This is plus 7. This is plus 6. This is plus 5. Plus 2. Right?
Mx plus b with b. Or,
If it's linear, it would be plus b, yeah. So this plus c is not there for decoration, right? It tells you important part. In terms of the previous example with speed, whether I throw from 7 feet or 6 feet, that will determine how far it goes, right? You don't want to put the like in the old age, you don't want to put the, right, when the ships are coming in to attack you and so on, you don't put the cannons on the beach, right? Because they go, you put them high up, right? They can go further, right? It's simple differential equations. They didn't know about it, but it worked. so right now you have this plus c. Now observe this. You might be given a point in space, and there is only one of the functions that would go through that point. So say there's a point in space right there. That point would have x comma y. But you can understand that point as y of x equals some number. So say that I was given that y of 3 is 90. Let's say this was given to me. I would be able to compute value for c, because what this is giving me is that x is equal to 3, y is equal to 90, plug them in and find c. You see that? This thingy over here is called initial condition. Should put that in blood. So 90 is equal to 3 cubed over 3 plus c. So c is 10, right? Oh no, it's not 10. It's 81. Is it 81?
yeah, nice.
That's what I said. Please pay attention. So now, what you have is y equals x cubed over 3 plus 81. And this creates a new creature called particular solution. Now it's the solution for that point. And you know this is pinned down, right? It has to go through that point. Plug in 3, you will get 90. This mathematical model is going to model something in the galaxy, right? And now we have a particular solution for it. So you can have a general solution if it's plus c. If you have initial condition given, you get to find particular solution. Problems 17 through 26 give you the differential equation, the solution to differential equation, and initial condition. So once you have general solution, you plug that there to make sure it works. If that is indeed solution, plug your 0 and 2 and figure out C. So 17 through 26, yeah, what else are you going to do tomorrow? All those, right? You practice you don't practice solving differential equations, but you definitely practice derivatives of all kinds. A lot of derivatives and a lot of integrals in this class. And then you are developing this skill to check your answer. And you're also practicing how to obtain particular solutions, which is figuring out what the value of C is. and then see whatever else you can do. There should be some exercises. Try to look into these word problems as well and see how good or how bad they are. Look at this one. It says the time rate of change of population P is proportional to the square root of P. My equation was Kp. Your equation over there is going to be K root P. How does that change the solution? Are you going to have exponential solution to the question? Hell no. Your solution is going to be a square root function. Because dp over p gives you ln. dp over root p doesn't give you ln in the integral, right? So changing something slightly here has profound, right, change in the solution. And the last piece of advice, guys, before you peace out is practice this course with what if. That was the perfect example of what if it's not Kp? What if it's K root P? What if it's Kp squared? What if it was sine x? And so on. Right? What are the ones that you can integrate, ones that you can't integrate, ones that Mathematica can integrate, right? And so on. So that's it for today. Let me just end this. Say bye, everybody.